Welcome to video on linear integrated circuits. In this video, we shall see the summary of triple five timer and op-amp and its applications. This is my email ID, and we have referred microelectronic circuits by Sedgwick Smith to prepare this video. So this is the triple five timer circuit diagram. So triple five timer consists of three resistors of equal value, that is R1, R1, R1. It has two comparators. It has the RS flip-flop. It has a transistor. So it is actually a 8-pin IC having pins like threshold, trigger, discharge, ground. We have output. Along with these two, there are two more extra pins. One is for reset pin for this flip-flop and one more extra pin for controlling the VTH. So as you can see from the circuit diagram, so VTH, which is called as a higher threshold voltage, is usually 2/3 of VCC if we are not forcing any voltage at VTH. There is one more voltage, that is VTL, which is the voltage at this point. It's always 1/3 of VCC if you are not forcing any voltage at VTH. The relationship between VTH and VTL is always VTL is half of VTH. We have for the comparator, since there is no feedback given, so it will be always operating in open loop. The output possible voltages can be plus Vsat or minus Vsat. Plus Vsat for this op-amp comparator is VCC, minus Vsat is 0 volts, and we have the general timer output will be equal to 0 if the threshold voltage is greater than VTH. If the voltage at threshold goes above VTH, then we have the output voltage as 0. If the trigger voltage goes below VTL, we have the output voltage going high. So this is the basis for using the applications of triple five timer. So we have the condition is that if the threshold voltage goes above VTH, then R becomes 1, then it resets the output goes 0. Similarly, if the trigger voltage goes below VTL, as it is written here, the set becomes 1. If set becomes 1, flip-flop will set, and then this will become VCC. That is the basic operation of the triple five timer. Now this is one of the application, monostable multivibrator. This is the circuit diagram. We have a resistor R and C which are used to decide the pulse width of the monostable multivibrator. As you know that monostable multivibrator is a circuit which has got a stable state and a quasi-stable state. The stable state of this monostable multivibrator is 0. Quasi-stable state is actually 1. So it will be always in the circuit will be always in stable state as long as there is no trigger given. A trigger voltage is 1 for this triple five timer. If the trigger voltage goes below VTL, then the output enters the quasi-stable state. It remains in that predefined time, which is given by T is equal to C into R LF3, LMF3, which happens to be 1.1 RC. The quasi-stable duration is decided by the values of R and C. When it will start the quasi-stable is decided by the trigger signal. It is most important that the trigger signal should go below 1/3 VCC, or in general it should go below VTL. So as long as the trigger voltage is at we'll see the summary of the working of this one, and the capacitor, once the trigger signal goes below VTL, the capacitor starts charging. It is charging towards VCC whenever it goes above VTH, since it is connected to threshold pin here. the output goes to 0 as the capacitor voltage tends to exceed VTH. So then the capacitor will discharge to 0 through transistor. So since the charging path is R and C, the time constant of the capacitor while charging is R into C. While discharging, it almost instantaneously discharges because the resistance offered by the transistor when it is on is very small. So what is the summary of monoshot? If the trigger is VCC, we consider it as stage 1, so it is not a valid trigger. The reset and set are 0, so output remains in the previous state of 0. The BJT is on because the BJT is getting the complement of V0 as its base drive. As you can see, this is getting Q bar. So BJT is on. For timing capacitor we keep on discharging. Suppose the trigger voltage goes below VTL, then set will become high. The set is 0. Now output will become VCC. Once output becomes VCC, BJT turns off. The capacitor now starts charging towards VCC. So assume that now it has not the pulse width is still less than the time is still less than the pulse width. So the trigger has been removed. Now you can see we are thinking of this. So once the trigger goes high again, if it is the pulse width is not elapsed the required time, so then both R and S will become 0. The transistor is, when it is 0 means it remains in the previous state. The output remains in the previous state. So previous state is high. The output remains in high state. The transistor is on. Capacitor is still charging. So when the capacitor is charging towards VCC, whenever it exceeds VTH, the above comparator will make the output as high. So R becomes 1. So S is 0. When R is 1, it will reset. The output will become 0. When output is 0, the transistor will turn on. The capacitor start discharging with a time constant C into the on resistance of the diode, which is very small. So this way we are going to summarize the monoshot working. To find the pulse width of the monoshot multivibrator, we have an expression like capacitor is equal to V final minus V final minus V initial to P power minus T by RC. So substituting the final voltage as VCC and initial voltage as 0, which is this is the initial voltage, the capacitor is allowed to charge up to infinite time, it will go to VCC, but at T is equal to T. So at small t is equal to this capital T, the capacitor voltage is reaching VTH, so which is 2/3 of VCC. By substituting those parameters, we'll get T is equal to 1.1 RC. Let us see what type of support if the trigger signal applied is something like this. So assume that I want to have a pulse width of 110 microsecond, but the trigger signal is having a high of 2 millisecond and low of 2 millisecond. As you can see, the trigger signal is low, that is less than VTL for almost 2 milliseconds. Suppose if you don't use a signal conditioning network, the the output will also be a 2 milliseconds. Since you want 110 microseconds, since we are using RNC as so now we need to first signal condition this circuit, this trigger signal before we apply to trigger. Now we need to obtain a trigger signal which is of something like this manner, so that we are having the trigger signal for a very short period going less than VTL. So once we could able to get such type of trigger signal from this square wave, then it is possible to get a desired output. Now we'll certainly get a desired output something like this, because now we can see it has initiated the trigger signal and it has gone back to VCC. Now the output is there for VCC for only 110 microseconds. The required circuit to do the signal conditioning is this. So we have this square wave applied to this capacitor resistant diode. So this is a differentiator clamping circuit and taking out the positive peak of this. Now this RD CD should be designed like that. So RD into CD should be far less than the time period of this trigger. So that's a very important condition. So this is the differentiator circuit with the output clamped to VCC, and we have a diode to ensure that we are removing the positive spike over here. If the diode was not used, the spike would have been gone up to 2 VCC. So we are restricting the height. So this is a signal conditioning network. So this trigger signal is signal conditioned using this one, and it is finally applied to pin number 2 of the trigger. So if you use this one, whatever the pulse width, whatever the width of the signal which is going below, so this will be taken care by this type of spike generator. Now it is also possible to vary the pulse width using the external voltage, that is VTH. So we'll just do the same, take the same equation. Now since the capacitor voltage will always charges up to VTH, now capacitor voltage at T is equal to capital T is not 2/3 VCC, but it is V external. So substituting those that particular value of VC and V external, we'll get the expression for time, which is nothing but R sin to ln of VCC by VCC minus V external. Now it is not no more ln of 3. Now depending on the external voltage, the pulse width changes. Let us have a look at the stable multivibrator. Now the name itself indicates that none of the states are stable here. We have the circuitry RA, RB and capacitor. Now this capacitor charges VCC through RA and RB, and when the capacitor wants to discharge, so it discharges through RB and the transistor Q1. So we have this is charging to VTH and it goes down till VTL, and this will be keep on continuing as long as the power supply is on. The other name for this circuit is pre-running oscillator. So we have the expression for the high time and the low time, that is on time and off time, given by this 0.69 C into RA plus RB and 0.69 C into RB. So where RA and RB are the resistors which are connected here. So RB is the one which is responsible for discharging. Both RA and RB is necessary for charging the capacitor. The operation is quite simple. So suppose the capacitor voltage is less than VTL, then set is high, then the output is also high. So transistor is off, capacitor is charging towards VCC. On its way to VCC, as soon as the voltage goes to VTL, both R and S become 0, meaning the output remains in the previous state. So capacitors keep charging towards VCC. Once it goes above VTL, the reset becomes 1. Once the reset becomes 1, output is 0. The BJT turns on, capacitor starts discharging. So on its way, of course, discharging towards 0. So as soon as it slightly goes below VTH, both R and S will become 0. So output remains in the previous state. Capacitors keep on discharging on its way down to 0. Whenever it goes below VTL, it again goes high. So meaning this is how it is happening. If it tries to go above this, the output goes low. If it tries to go below this, the output goes high. This is how the astable multivibrator works. In this particular astable multivibrator, so as we know that TH is always greater than TL, because we have this RA plus RB. Here it is only RB. We cannot get duty cycle less than 50%. To get duty cycle less than 50%, we are supposed to bypass this transistor RB while charging. So this is what the expression is. While charging we have only RA, but while discharging we have RB. So because we are assuming that the diode resistance is very small, so we can get any duty cycle by choosing the appropriate value of RA and RB. We can also get a VC out of this by applying an external voltage to that VTH. So we have this is the expression for T on. We'll see in the next video in detail how does this works.